So I'd like to thank the organizers for giving me the honor of presenting this talk in memory of Professor Nambu, who was my PhD advisor. It was not very easy to work with a genius, but it was sometimes hard to understand. As Peter said, sometimes you never know where all these things are coming from. But one thing he did manage to instill, I think, in all his students is he managed to shape the taste of physics. I think that certainly I'm extremely grateful to him for all the knowledge he had imparted me. What I'm going to do is to give you a summary of some work which I have been involved in over the past couple of years with Robert Myers and Damian Galante and Diptarka Das and Krishnendu Sengupta, which is going to come up soon. And this problem actually is a certain aspect of a very general problem which cuts across many areas of physics. And this is the problem which I'll generically call a quantum quench. So the specific context in which I will be discussing this is a problem of a system which, how does this work? Center button, okay. Oh, the other way, sorry. So the specific context I'll be talking about in this problem is a time-dependent coupling in some general field theory. We'll take a relativistic field theory in particular. I'll be mostly talking about a time-dependent coupling which is a relevant perturbation of a critical theory for reasons which will become clear pretty soon. And the question is very simple and very general. This coupling has a form which goes between constant values and passes to zero. When the coupling is zero, the theory is a critical theory. And the question is that if I initially prepared the system in its ground state, I want to look at what happens because of this time-dependent coupling, what kind of excitations, and whether I can learn something interesting about it. And the reason why I'm concentrating, now this problem is of course a very general problem and it has many different dimensions to it, as I said, in many areas of physics. I'm concentrating on this, the fact the unperturbed theory is a critical theory, is because one has an expectation that as the coupling goes from one constant to another, if I look at various times in between, the response to this time-dependent coupling could have and should have some universal features which are associated with that critical point. One of the earliest examples of such universal behavior was discovered in the 1970s by Tom Kibble, who looked at the problem of defect formation in cosmology. As the universe cools down, there could be phase transitions which leads to defects. And Kibble asked the question, can I estimate in a very robust and model-independent way the number of defects, which are defects like monopoles or domain walls or things like that, which are formed in this process. About 10 years later, Zurek realized the same considerations can be used in condensed matter systems. And in more recent years, this entire way of thinking has been applied to cold atom systems, other condensed matter systems, what have you, many of which I don't know very much about. The particular regime in which the Kibble-Zurek, nowadays called the Kibble-Zurek mechanism, works is when the quench is slow compared to an initial mass cap. So here what one starts out is a coupling which is non-zero, and so therefore the theory is massive. The value of the coupling decides the mass scale, and the time during which it changes, the inverse of which it gives the rate of the coupling, is the time is much larger than the mass scale in the theory. So in that case, when the coupling is very slowly varying, it's very far from the critical point. As one would expect, there is a pretty boring adiabatic time evolution, which one can calculate by usual methods in quantum mechanics. But as it approaches the critical point, of course, the instantaneous correlation length becomes very large, or the instantaneous mass gap becomes very large, and adiabaticity is inevitably broken. So with a set of very simple assumptions, which may or may not be well justified, what Kibble and Zurek assumed is that soon after the adiabatic evolution is broken and the system starts getting very excited, let's assume that there is a regime in which the evolution is actually completely diabatic, namely the system at minus TKZ, which is called the Kibble-Zurek time, is frozen till it emerges out again. And then you sort of look at the subsequent time evolution. A slightly better approximation is, in fact, provided in terms of scaling functions. Namely, so one of the consequences of that, and an assumption that the instantaneous correlation length is the only scale in the theory, leads to a hypothesis of scaling hypothesis, where like one-point functions basically scale with the conformal dimensions of this operator O. Delta is the dimension. Two-point functions of a similar scaling, where all the quantities which appear are the quantities which are like the instantaneous correlation length at the Kibble-Zurek time or the Kibble-Zurek time itself. So these are the expressions for these quantities which can be easily calculated. And as I said, in systems which have quasi-particle behavior, the scaling of, for example, defect densities also follow from this kind of reasoning. And nothing very much more is known for strongly coupled systems. It turns out that scaling a different kind of scaling behavior is in fact known in the completely opposite regime. And the completely opposite regime is a coupling which sort of suddenly drops down from one value to the other. In particular, a coupling where the final value of the coupling is 0, so the theory is actually critical. So you start with a massive theory and you suddenly drop down to a critical theory. In this case, when the system is in 1 plus 1 dimensions, Calabrese and Cardy, in a series of quite celebrated papers, argued that there is a description of the Quench state in terms of a particular class of states in the conformal field theory, which is described by the final Hamiltonian. And using powerful methods of two-dimensional conformal field theory, they could derive a set of pretty universal results for various quantities. I'm just displaying one of those results. Consider some operator which is not a conserved quantity, but some generic operator. So you would expect that it relaxes down to some 0 value after everything is done. And so what you notice here, so the relaxation time itself is not universal. It contains a parameter tau naught, which is basically like the inverse of the mass gap of the original theory. So that depends on the microscopics. But if you were to take ratios of relaxation times for different operators, that ratio is completely given by the ratios of the conformal dimensions and therefore universal quantity. Apart from these kind of things, there are a whole host of results which are known for this 1 plus 1 dimensional theory, very interesting results for the growth of entanglement entropies and various other things, but nothing general is really known in higher dimensions. So over the last few years, as I'll describe a little bit pretty soon, some amount of, I wrote here considerable, I'm not very sure, but some insight into such universal properties have been used has been obtained by using the ADS-CFT correspondence in understanding such process. And I'll describe how one goes about using the ADS-CFT correspondence for such a process. And along the way in this program, which many people have participated in, the holographic methods have actually led to a new universal behavior which was not known earlier. And this universal behavior happens in a regime which we call a fast but smooth quench. So here the time scale is much smaller than the inverse mass gap. So this is the opposite of the slow quench regime. But it's not as small as the UV scale of the theory. So there is this intermediate regime, and as I'll describe, in this regime, there is again a robust set of scaling relationships, which I will talk about in detail later on. So this new universal behavior was discovered by looking at this problem using techniques of the ADS-CFT correspondence. It turns out, as I will show, that this universality is in fact a general property of any field theory, and it has nothing to do with special properties of field theories which have holograms, which are described by weakly coupled theories of gravity. So let me very quickly describe the general setup where this came about. The ADS-CFT correspondence provides a duality between a large N quantum field theory, which are deformations of conformal field theories. This is exactly the kind of things we are looking at. And theories which contain gravity in asymptotically anti-de Sitter space. And the general picture is that the field theory lives on the boundary of the space, while the dual gravitational theory lives in the bulk. And there are many lucky situations when the quantum field theory is strongly coupled, and the dual gravitational description is in fact classical general relativity. And it is in this regime where I can actually calculate things, because a strongly coupled problem in the field theory maps into a classical problem. The main ingredient of why this can be used in the quantum quench problem is the fact that the coupling of the field theory this is a part of a more detailed dictionary, which I'll not talk about, and this is the only thing which you need to know, is that the coupling of a field theory becomes a boundary condition of the dual bulk field. So as a result, the problem of a time-dependent coupling in the field theory becomes a classical problem of evolution where you have imposed a time-dependent boundary condition, which by itself is not an easy problem to solve, but at least it is easy to state and easy to formulate. So therefore, if we were to study quantum quench, which involves a critical point, we have to identify a bulk theory which is dual to a critical point. And we have to impose the time-dependent boundary conditions of the bulk fields for the dual relevant operator. And then we calculate the response. So it's very much like taking a tin can and banging it on the boundary. Being a gravitational theory, it's going to something happen. Is this working? Yeah. Oops. It's pretty rapid. Oh yeah. Okay. And so a disturbance goes into the bulk, and it does something, and that's something from which you're going to extract the response of the theory, which would be one-point function, correlation functions, or what have you. So this is something which we initiated some time ago, and these are some of the papers from your collaborators. I'll not go into the details of what we actually achieved, except just to say that we were able to look at this Keeble-Zurek kind of phenomena using this kind of framework. And one of the things which we learned is that, so as I said, the troublesome region when you do a very slow change is the time when you cannot use adiabatic perturbation theory anymore, being close to the critical point. What we found, so the lack of adiabaticity means that a power series expansion in inverse powers of the time scale has broken down. So there is no Taylor series expansion, because adiabatic expansion is an expansion in time derivatives. What we found is that there is a new expansion which appears, which is valid for large delta t inverse, but it appears in the fractional powers of this. To leading orders of this expansion, the dynamics is dominated by a certain zero mode, which simplifies the analysis of the bulk response. The zero mode dynamics has a scaling solution which shows this Kibble-Zurek scaling. And we were able to vindicate this analytic understanding by explicit numerical solutions. So following this, there was an interesting work by Bushell, Lehner, Myers, and Van Niekerk, who looked at, again, the opposite regime of this process, namely when the time scale is small compared to the gap rather than being large compared to the gap. Okay. So what they did is exactly what I started out with. You start out with some in the boundary language, a conformal field theory, in the bulk language, and initially pure ADS space, and then you turn on a coupling which saturates to some final value. So what they found, first by a detailed numerical relativity calculation, and then which was later supported by some intuitive arguments in the ADS-CFT correspondence, is that various quantities like the response, the one-point function of this particular operator being quenched, seems to have a universal scaling with the rate of that quench. And so, and the same thing is true, for example, for the energy which is produced in that quench. Now, this result was a little bit puzzling. And the reason why it is puzzling is because if you notice the powers, the power which appears here is the dimensionality in which the field theory lives, and delta, which is the conformal dimension of that operator. The operator is a relevant operator. However, when delta lies between d and d upon 2, it appears that everything is blowing up. I mean, the one-point function blows up, the energy blows up. And this seems to contradict these known results, for example, of Cardi and Calabrese, which corresponded to a completely sharp and sudden quench, which should have meant that delta t is going to 0. So for a while, many people thought that these results, which were obtained in this holographic analysis, are properties of some special strongly coupled field theories, and who knows what those theories are, and which have these gravity duals. But this was not quite believable to us. So what we decided is that, well, let's look at, just forget about holography, forget about where it comes from. In normal quantum field theory, can we look at this problem and decide what's really going on? So that's the work I'm going to describe. So we embarked on it and landed up in something quite interesting. So we started out with the the theories which have holographic duals are strongly coupled theories. And so in a good spirit, we said, okay, let's start at the opposite extreme. Why don't we consider free field theories? Free field theories like a scalar or a fermion with a time-dependent mass. And let's try to find these functions, m of t, the profile of the time dependence of the mass, so that we can solve the problem exactly for all values of the quench rate. Well, relativists have actually looked at this problem. This is a classic problem of particle creation in cosmological spacetimes. So there are known examples, or if you, with a little thought, you also realize this is also just a standard problem in Schrödinger quantum mechanics with thinking time as the space. It's a problem with potential. So you look through flip through books and try to find exactly solving problems in quantum mechanics, for that matter. So these are there are many such examples. There are some examples of these mass functions for which you can solve the problem. So what do you mean by solving the problem? So what we mean is that if I were to decompose for example, that scalar field in terms of modes, the standard modes, and choose the modes which are in modes, namely they become standard plane wave modes at t equal to minus infinity, exact solution means that I know what these functions are, really. And so in the cases which I have described, the functions look like this. Don't look that interesting, but nevertheless, you can put those in Mathematica and see what they look like. So that's precisely what we did. So we started with this, and then we calculated the response. The operator which is being quenched is the operator phi square. So we calculated this object. But of course, this is a quantum field theory. It's a free theory, but nevertheless, this is a composite operator, so it is ultraviolet divergent. So we need to renormalize. So we have to subtract some counter terms, and there are well-known and well-established ways of finding what those counter terms are. And then you calculate what the renormalized quantities are. And here is a typical, just putting in this hypergeometric stuff in Mathematica. And here's a typical example of the kind of results which you get. So this is a picture of the renormalized expectation value as a function of time at different values of the rate. And you can see that it gets larger and larger as the rate increases. And this is a corresponding picture of the energy, how it sort of accumulates as a function of time. So that's nice. The great thing is that when you take the limit of what we call the fast quench, namely the time scale being much smaller than the inverse mass of the theory, one could actually look at these expressions and extract exact analytic results. And I've just displayed some of these exact analytic results for different dimensions. And if you look at these results, you immediately realize that they are consistent with what was found in these holographic things. The holographic results had some powers of delta t, which was d minus 2 delta, and sometimes there would be logs. And if you look at these are, in this case, this delta was basically d minus 2, and all these time derivatives basically translate to some powers of delta t. Okay. So you might think that, well, it looks like that this kind of behavior is valid for those strange field theories which have holographic duals. They're valid for these trivial field theories which are free field theories. So could it be that this is actually a general result in quantum field theory? So that's what we decided to investigate. And the answer looks quite embarrassingly simple. So here is how it works. So as I said, you start with a conformal field theory with a relevant perturbation, and the perturbation has a time scale which is delta t. I'll in fact take the perturbation of any very quite generic, with the condition that, say, it vanishes for some time less than 0. So it starts doing something at t equal to 0, and there is up to some time delta t, after which it goes to a constant, and the initial and the final values could be the same, could be different. I'm just taking the case when they are different. Of course, you need to smooth these things out. And the condition is that this time scale, which is the inverse of the rate, is small compared to all the other time scales which are in the problem. The only other time scales in the problems are those associated with the values of this coupling. So it's smaller than this delta lambda raised to the something, or delta plus, which is the maximum value, or lambda plus or lambda minus, or what have you. So this is the smallest time scale in the problem. And imagine start computing this object in good old-fashioned perturbation theory. So here are the first few terms in perturbation theory. So this is the response, the expectation value of the operator, which subtracted with the expectation value of the initial value of the coupling. And the first term is the well-known linear response term. The second term contains some 3-point functions, and so on. The object which appears here, as is known in standard textbook material, is the retarded Green's function of the initial theory. So this is some commutator of those two operators multiplied by a theta function, which makes it the retarded Green's function of the initial theory, where the value of the coupling is lambda naught. And all the quantities we assume are renormalized quantities, so all the UV stuff is already taken care of. So look at the first term in this, the linear response term. It has an integral of a retarded propagator. And we want to, while the integration over the space which appears here has been written over the entire space, causality actually implies that only the region which is, if I'm going to measure the response at some time t, you draw the past light cone from that, and the integral which appears here is only the part which lies in that light cone. So therefore, if you want to calculate this quantity right after the quench, which is the t equal to delta t, the maximum extent of this integral over x prime, the x prime goes only from like 0 to delta t. However, by assumption, delta t is smaller than all other physical scales in the problem. So therefore, the Green's function at the initial value of the coupling lambda naught is basically the Green's function of the conformal field theory which lives in the ultraviolet. So you can replace to first order that Green's function by the Green's function of the conformal field theory. This means that in the leading contribution, the only scale that appears in the problem is in fact delta t. So therefore, you can write that expansion as an expansion in terms of a dimensionless coupling. This delta lambda is the change of that coupling, which I've multiplied by an appropriate power of delta t to make it dimensionless. And this just accounts for whatever dimensions which is in there. And of course, when you look at the first term is exactly what you had expected, that universal scaling law. So there's a similar argument for the energy density which is produced. And since the coupling remains constant after delta t, this quantity is in fact the net energy which is produced in the process. Note that the result is independent of most of the details of the theory, and it depends only on the properties of the conformal field theory which lives in the ultraviolet. So what happens to this problem of delta t going to 0 and things blowing up? Note that we have been dealing with renormalized quantities, which are of course useful when the scale is much, much bigger than the UV scale in the theory. And of course, strictly speaking, an instantaneous quench means that delta t is in fact of the order of the cutoff scale in the problem. So the renormalized quantities, you might think, are not expected to yield answers in this limit. However, one way to examine this connection in detail is in fact to look at ultraviolet finite quantities and look at regimes where you expect the renormalized quantities to make sense. So let's go back to some free field examples. So one example of an ultraviolet finite quantity is the excess energy which is produced in the process, which is defined as the energy at very late times, and what I subtract out is the ground state energy for the final value of the coupling. So this is the excitation energy as measured at very late times. And here are the results for what happens this is the example of a free, I just give an example of free scalar field theory. So what you note here is that as you take delta t going to 0, whether this quantity approaches a finite limit or not depends on the dimensions. Like in dimensions 2 and 3, it does approaches a constant value, and that in fact agrees with the instantaneous value as it should. Whereas when the dimensions become 4 and 5 or higher, this actually diverges. For those values, if you were to compute the instantaneous change, for the instantaneous quench, they also diverge. So it's actually quite consistent. Another interesting quantity which actually shows the real regime in which this thing is worked is a 2-point correlation function. So if you compute the 2-point correlation function at a given time for different values of the spatial separation, we find something very interesting. So here is a plot of the 2-point correlation function as a function of the inverse rate for different values of the spatial separation. And what you notice is that when the time scale for the quench is small compared to the distance scale, which separates out the 2 points, the results become independent of the rate, and they, in fact, approach the values of this instantaneous quench. When the time scale is very large, that's not the regime which we would call a fast regime, but there is this intermediate length scale where delta t lies between what you would call a very slow quench and a very, very fast quench, where it has a scaling behavior which is precisely the scaling behavior of the renormalized quantity phi square. So this gives a much more detailed understanding of the validity of this kind of scaling. How does the scaling relations, so we have shown that there are well-known results which were known for slow quenches, and there are some new set of results which are being understood for very fast quenches. And you might wonder whether there is a smooth interpolation between these two kinds of quenches. So we therefore again looked at some solvable examples. We don't have any good result in generality. So let me just show you what happens. This is an example, for example, for free fermions. Free fermions with a time-dependent mass, where this operator is plotted as a function of delta t, and as delta t increases, you see that it goes from the fast, smooth scaling to the Kibble-Zurek kind of scaling, and eventually to an adiabatic answer. So there is no abrupt jump in what goes on. I'm running out of time, right? Okay, so let me skip something. So the other thing which I wanted to tell you about is how these things, what one can learn from actually performing these things in concrete lattice models, namely with a finite cutoff, but let me skip that and conclude by saying that I have concentrated on a very particular problem in quantum quench. There are a large number of other very interesting issues, particularly issues which involve thermalization and chaos in this kind of process, which has witnessed an impressive progress in recent months. One interesting aspect of this entire subject is that much of the progress in this area draws from concepts, some tools from many diverse areas of physics. So I thought that these are examples which are progress made from cross-fertilization across various areas of physics, very much in the spirit of Nambu's taste of doing physics without boundaries. Thank you. Before doing that, I'd like to advertise an obituary which myself and Spenta Wadia wrote for Nambu, which was in CERN Courier. I would invite you to have a look and send us your comments. Thank you.